Welcome to solverfy.
So we have a metal cylindrical conductor inside which there is a non-conducting cylindrical object with charge density rho. But it is not at the center. The center is somewhere else. Now we want to find the field at a distance r from this point, from the center of the cylindrical shell. So let's look at it this way: the cross section of this system. This is our cylindrical shell, and this is our cylinder with charge. Now, because it is not at the center, it will induce a charge on the inner surface of this cylinder, but it will not be uniform. There will be more charge close by and there will be less charge farther away. Now, because there should be no field inside the cylinder itself because it's metallic, it means that the total charge enclosed by this surface must be 0, which means this induced charge must be equal to the charge on the cylinder itself. Now, because the cylindrical shell was initially neutral, there will be negative charge induced on the outer surface. Now, this must be equal to the positive charge induced on its inner surface, but it is not affected by what's inside, which means this charge will be distributed uniformly. Hence, we are back to the problem of uniformly distributed cylindrical distributions. We've seen that the electric field due to such distributions. So let's talk about that. Let's say this is our outer conducting shell, and there is an inner cylinder inside and so on, but we don't care about that. Now let's say this length is R, L. We consider a Gaussian surface, another cylindrical Gaussian surface of, let's say, radius R. Now, we use Gauss's theorem. The flux induced will be the electric field times area. The area of this cylindrical surface will be E times 2 pi R into L. Now, this is equal to the charge enclosed divided by, but we know that the charge enclosed will be rho times the volume of the cylinder, and the volume of the cylinder would be, because the radius is R1, the volume of this cylinder would be the surface area times the length, which would be pi R1 squared L divided by epsilon naught. Using this formula, we can see that E is equal to, we cancel pi and L, and we see that our answer is rho R1 squared divided by 2 epsilon naught R. I'm sorry, cancel the L instead of R. The L gets cancelled, the R stays the same, giving us this solution.